Hello and welcome back. We are in the middle of studying just an introduction to differential equations, and today we're talking about separation of variables, which, if you've been with me for a little bit, you've actually already seen. Our learning objective for today is to separate the x stuff from the y stuff in order to integrate and find a solution. Equations where all the x terms can be collected with dx and all the y terms with dy are said to be separable. The solution procedure is called, shocker, separation of variables. So we're just going to dive in with some examples. Find the general solution for each of the following. So A says dy dx equals 2x over y. Now you'll notice here I've got y stuff and x stuff on both sides of the equation. And that's what I don't want. I want all the y stuff on one side and I want all the x stuff on the other side. So if I take this dx and multiply it by both sides, and then I can take y and multiply it by both sides, then I'm like essentially combining like terms. So what we have here then is y dy equals 2x dx. All the y stuff on the left, all the x stuff on the right. And now I can integrate both sides. So the antiderivative of y dy is 1/2 y squared, and the antiderivative of 2x dx is x squared plus c. Don't forget your constant of integration there. And then the last step is just going to be to solve for y. Get just y or maybe y squared by itself. So y squared equals 2x squared plus c2. Where did that c2 come from? Well, my original constant of integration was just this c here, right? But when I was isolating y, I multiplied both sides by 2. So I still have a constant on the other side, but it's a different constant because it's been multiplied by 2. So this 2 here on the bottom means it's a new constant, but so I'm just keeping track. It's the second constant now that I've used. All right, part B. dy dx equals y squared. Again, we need to get all the x stuff on one side and all the y stuff on the other side. And just for consistency, I keep the y's on the left and the x's on the right. And then we'll integrate both sides. In order to integrate 1 over y squared, though, I'm going to go ahead and rewrite that first as y to the negative 2. Now I can take the antiderivative of both sides, and I get negative 1 over y equals x plus c. And then finally, I'll solve for y. And I get y equals negative 1 over x plus c. Okay, let's keep going. Let's do another one. dy dx equals xy. All the x stuff on one side, all the y stuff on the other. Take the antiderivative of that. Oh, this will be fun. What's the antiderivative of 1 over y? That's ln y. And that equals 1/2 x squared plus c, constant of integration. Now we need to get y by itself, so we're going to exponentiate both sides, and we get y equals e to the 1/2 x squared plus c. And make sure that that c stays with its little family here. This does not equal e to the 1/2 x squared plus c. This c needs to stay up here with his friends. Okay, next one. We've got 4y y prime minus 3e to the x equals 0. Okay, so let's get all the y stuff on one side and all the x stuff on the other side. And you'll notice here that I changed, just for my own brain, y prime into dy dx, okay? And then I can get 3x dx over to the other side. And then we can take the antiderivative of both sides. And we get 2y squared equals 3e to the x plus c. And we can stop there, but let's go just a little bit further for fun. So we'd get y squared equals 3e to the x plus c divided by 2, the whole thing divided by 2. And then y, of course, would equal the square root of that whole thing. Example 2, find the solution of the differential equation that satisfies the given condition. So same process here, it's just that now we have an initial condition, and so we're going to have to solve for c. So we're going to get all the y stuff on one side and all the x stuff on the other side, but we don't actually have any y's. It's all in terms of t this time. So that's fine. We'll just put all the t stuff on one side and the x stuff on the other side. And I put the t stuff on the right this time because I'm differentiating in terms of t. And that's the stuff that I want on the right. Okay? All right. So we'll take the antiderivative of both sides. So we get 1/2 x squared equals e to the t plus c. And this might be a little confusing because this time the x is where we're used to y being, right? And the t is where we're used to x being. So this 0, when I solve for c, that 0 is going in for t, and the 1 is going to go in for x. So 1/2 1 squared equals e to the 0 plus c. 1/2 equals 1 plus c, so c equals -1/2. And then you can pop that back in. You get 1/2 x squared equals e to the t minus 1/2. These are starting to look complicated, aren't they? Okay, dy dx is on the bottom. So our variable of integration is x. So all the x stuff is going to go on the right. And just be careful to keep in mind your domain here because see, we've got an xy on the bottom. So keep in mind, x can't be 0 at the end of this and y can't be 0 at the end of this. So it may take me a couple of steps here to isolate the x's and the y's. Let's start by moving the dx to the right and the xy to the left just to get rid of that fraction. So we've got xy dy equals 1 plus x dx. Now I can divide both sides by x. Now I'm good. I've got all the y stuff on the left, all the x stuff on the right. And anti-differentiate both sides. This guy is a little bit complicated, so let's split that up into 2 different integrals, shall we? So we've got 1 over x plus 1. That's a little bit better. And we can just take the antiderivative of each of those separately. So we've got 1/2 y squared equals the natural log of x plus c. And then we can plug in our initial condition. So the x's are 1 and the y's become -4. All right, well, the ln of 1 is 0. And 1/2 of 16 is 8. So we end up with 8 equals 1 plus c. So 7 equals c, and pop that back in. And again, just keep track of your domain here. Remember, from the beginning, x couldn't equal 0 and y couldn't equal 0. Okay, here's another one. dy dx equals y over 2 root x. I feel like we need to do some rewriting here. So I've divided both sides by y, multiplied both sides by dx, and then this 2 here, see that guy? Just pulled him out. And then the square root of x became x to the -1/2 because it was on the bottom of that fraction. So pause if you need to, just make sure that second line makes sense to you. And then we can take the antiderivative of both sides. So the natural log of y equals the square root of x plus c. Now, we have to isolate y Okay, it can't be stuck here within the natural log. We really have to get y in its own right. So we can exponentiate both sides like we did before. And again, look at this c stays up here in the exponent, okay? So we've got e to the natural log of y equals e to the square root of x plus c. Now, e to the ln y, that was the whole point of exponentiating. You get y equals e to the square root of x plus c. Now, let's pause for a moment and look at this, because this is going to come up later. You can stop here. This is totally fine. However, we can actually rearrange this a little bit more, because this constant, well, it's interesting. So y equals e to the square root of x plus c is the same thing as y equals e to the square root of x times e to the c. And e is a constant and c is a constant. So e to the c is still kind of an arbitrary constant. So we could actually rewrite it as y equals e to the square root of x times c. And if you want to keep track of the fact that this is now the second constant we've been using, let's put a little 2 there. And then this c, I mean, if it's multiplication, I could just stick it up here. So I could have y equals c2 e to the square root of x. See how all that works? So actually, let's go back up here for just a second. This c from the beginning, if you've got a plus c in the exponent there, you can just bring that forward. So y equals ce to the square root of x. Interesting stuff, huh? These two are the same thing, just different forms. Now we can solve for c. So plug in 1 for y and plug in 4 for x. And c equals e to the 1 over e squared. Okay, and plug that back in. Now, what if we had stopped and solved for c up here? Let's just go ahead and do that real quick and see what happens. So y is, we'd get 1 equals e to the square root of 4 plus c. All right, so that means 1 equals e squared plus c. So now to get that c out of the exponent, goodness gracious, I'm going to have to take the natural log of both sides. The natural log of 1 is 0. Okay, and then so c equals -2. So if I plug that back in, I'd get y equals e to the root 4 minus 2. Is that the same thing as this? Yep, it actually is, because that's the same thing as e. Let's see, to the square root of 4 times e to the -2. And look at that. See, those match. So you can do it either way, but just be careful about where you put that c and where you stop to solve. So anyway, good stuff, good stuff. Thank you for being here, and I'll see you next time.